All right. So welcome back. Welcome back to this channel. So in the last video, so in the last video, we have I have laid out uh I have laid out the basic foundations of stable diffusion, what stable diffusion actually is, and we have also looked at model we'll be using and a technique that we'll be using to actually decrease the computational power necessary to actually train the stable diffusion model. We have looked at both of them. In this video, we are going to discuss some more theory, a little more. Then we'll be discussing how we could actually generate, like, how can we control the output of a stable diffusion model? Because as we have looked at the demo in the last video, we have um, inputted the prompt that we want the model to generate, and then the model will generate the image, right, from the prompt. So how could we actually you do that? I mean, it is actually pretty simple, right? We'll just input the text embedding, but we'll look at like some more, look at it in, like, we'll use a little more different model rather than just text embeddings. We'll learn about that also, right? We'll be learning about that, the loss function, and that I think that's it. We're going to cover that for this video. So let's get started. So again, I'm going to repeat what I have told you about stable diffusion, right? So stable diffusion is a technique in which we could generate new images, right? So the idea is, while training or before training, this is how we'll, for example, train the model. For example, if we are dealing with handwritten digits, for example, generating handwritten digits, then you'll get like many numbers, right? Let's say this is 2, 3, 4, and all that. So let's say we'll have many numbers like this. So, and then what we'll be doing is we'll be adding random noise, right? We'll be adding random noise, and then we'll getting an output like that. So for something we are going to, for some images we are going to add more noise, and for some we are going to add less, and then something like that. And then for some images we are going to just like add in a lot of noise, just to make sure that the model is actually comfortable with generating like images, right? We'll be adding noises like this. So the input of the model that we'll be training is a unit that will take this noisy image. This will be the input of the model of the unit that will be training, and this will be the output. It will actually generate the noise that we should subtract from this image to get this image. So that is the idea. And then by training this model, we could actually use it on random noise and let the model find patterns in this that look similar to, let's say, a digit. And the main example, and the very good example is, when like children looking at clouds and finding different patterns, even though there are none, and like they'll find some patterns in the sky, right, or in the clouds, right? So that is one thing. And the model will be able to, like, generate random, or find some patterns in that noise that may look like an original digit in this case. So that is the idea, right? And then how will we train the unit? Well, we'll take a unit. We'll take this image, not this image, of course. I'm going to come back to that. We are going to take this image, these images, right? So this will be the input. We're going to take this into the unit, and the unit is going to predict all of these values, right? We're going to predict all of these values, and the loss function, there is nothing special with loss function. The loss function is essentially going to be it mean squared error between the original noises that are added to the input image. The mean squared error between the original between the original noises, right, and the predicted noises. So we'll just do like a mean squared error, and then we could find the like loss for noise, like the difference in the noises that is actually predicted. So that is the unit architecture. The main model will be taking this noisy image, and try to find patterns in the inference time. In the training time, we'll just do like normal mean squared error, right? We want the model to actually generate the actual image. So this is training data, right? Now we have also used the autoencoder, right? Just to make sure that the images is not like computationally very hard for the model to process. Hi, sorry for the little disturbance. This is the dog again. Okay, so let's get started. I think where I have left, yeah, we'll be doing that. So we'll be training an autoencoder, right? Just to make sure that it is not computationally costly for the model to actually train. What we'll be doing is we'll just take that image. We'll just train an autoencoder, autoenc, which takes in the image. It tries to regenerate that image, and in between we are going to have like a latent vector, right? So it is going to be something like that. So this will be like this will be the latent vector, right? And then by taking this, so we'll just train a model like this. So the loss function is going to be the mean squared error between the input and the output. So we just want the output to be as close as possible to the input, just to make sure that we are regenerating them and all the patterns are actually carried in the latent vector. And then after training it, we can just like take this part, take the encoder part, right? And we can just pass in the image and just get the latent vector. And remember, after predicting the model, the unit is actually going to predict the latent vector. The unit is going to predict the latent vector, not the actual image. And after that, we'll also be needing the transform autoencoder decoder, right? See that? We'll also be needing the autoencoder decoder to actually taking the output latent vector generated by the unit and predict the image or rebuild that image, rebuild that diminished image, right? That is the idea of using autoencoder while training stable diffusion. And the next thing we want to do is, of course, we want to add some type of condition or some type of prompt based on which the model can, we want the model to actually generate new images, right? So now, until now, we have used the example of like digit generation, handwritten digit generation. But now let's just move on to maybe something like a normal high level diffusion model that can generate any type of images. For example, like the original stable diffusion model, a model that can like generate any type of images, right? We have experimented about that also in the last video, and we have got some very good results. So we're going to solve a similar problem and introduce ourselves to the idea of conditional generation in stable diffusion. How does that work? Well, this is how it will work. So we're going to have two models, not one, but two models, because we want the text to be as close as possible to the image. Right? We're going to have two models. One is we're going to have like text encoder, and then we're going to have image encoder. Right? Both of them could be like CNN, could be any model, could be a neural network. It will be a neural network. I'll probably draw a three-dimensional block here. Right? It will take so the text encoder model is going to take in a text, take in T, let's say, and predict a random vector or predict a vector that has meaning, that carries meaning from this text, and these are numerical values, and it will take in text data, and the image encoder will take an image and also predict a feature representation of the same size. For example, we have for example, when we are downloading images from the internet, right? For example, let's say I'll draw some images. I'll probably try to, let's say, all right. So let's say we want to download this image from the internet. While downloading, we'll have a link called something like href or something, right? We'll have a description of this image, right? Sometimes we'll have a description of this image, and we are only going to download those images from the internet or the vast data. We're going to download the images that have like a description. For example, a happy boy. So the description is actually going to be the happy boy. Then let's say we have another image, maybe a dog, something. I can draw a dog, but yeah, something like that. What dog? Skinny dog. And then let's say we have another photo of it's a landscape, like sun, right? And then beautiful river, right? Maybe a boat. Yeah. And then let's say this has a description while downloading this image. Maybe this image has a description of, let's say, a beautiful scenery. For example, let's say we have like these three images. These three images. So what we'll be doing is next we'll be taking this text image, text data. We'll be passing this through this text encoder. We'll be taking this image of the boy, or the image. We'll be taking this image and pass that through the text encoder. So we'll be image encoder, right? So we'll be taking both of these pairs and pass them simultaneously to both of these encoders. The text to the text encoder, and the image to this image encoder, right? And then we'll do that for all of this data, all of the pairs. And then the main idea is we want the output of this text encoder for this data. For example, for this pair of image and text, we want the output of this image encoder for this image should be similar to the description, the output of this text encoder for this description for this pair, right? For the first pair, this is the first pair, right? This is the second pair, and this is the third pair. For the first pair, we want the output of the image encoder for this image to be as similar as possible to the output of the text encoder for this description. And how can we make sure that both of these vectors are similar? So that is the idea, right? We want both of these vectors, when inputted, both of these pairs, to be as similar as possible. How can we make sure that both of these similar? Well, yes, dot product, right? So we'll be performing element wise multiplication. We'll be multiplying them element wise and just add all of these outputs, and we'll get a single numerical value determining the similarity between these vectors. And if they are more similar, then it is good, right? And I'm going to come to the last function in just a bit, right? And then just like that, we are going to input both of these data, both of this data of the same pair to this text encoder and the image encoder respectively. So this image will go into the image encoder, and this text will be going into the text encoder. We'll get a vector, right? So we'll be having neural network, either a CNN or a RNN, or right. But we just have to make sure that the outputs are of the same shape. And then as we go on, as we train the model, right? Currently, as these models are not trained, right? We are assuming that these models are not trained. So these vectors are going to be completely random, and there is going to no, there is, there will not be any type of similarity between both of these vectors. But as we train our model for over multiple epochs, we are going to have we can observe some beautiful patterns and similarities. So yeah, the same for the second pair also. We'll be inputting this image to the image encoder and this text to the text encoder, and getting this values and comparing them and all that. And the same for this pair also, the third pair. So that is the idea. So we want the model, the difference between, or we want the output encoder of both the text encoder and the image encoder to be as similar as possible. And then we'll have weights, but the idea is, that is the idea, right? So now this leads us to finding a loss function. How can we actually determine the loss function? Right. For that, will you actually use something called clip loss and loss function, something like that. I think clip loss function, in which this is what we're going to do. We are going to take each of this image. I'm going to take this image. I'm going to draw it like diagrammatically, just to make sure you understand. I'm going to like draw this, take this image, not draw this image. So I'm going to take this exact image while training. So this is actually training, right? We'll be having the actual image. And again, while in the inference time, this is going to be the noised image, the noise input image, right? So sorry, we are not going to use the image encoder in the inference time. I'm very sorry. I'm very sorry, because the input we are going to pass it to the unit, right? And then yeah, so therefore forget about the image encoder for the inference time. So we'll be taking these images while training time. So this is the training data, right? We'll be taking these images. I'm going to just copy them. And then a beautiful scenery. Like that, right? I'm going to get like all of these values. I'm going to say, just like we have seen in the attention mechanism, right? Before like performing the attention, we'll be calculating the attention of both of these values. Will kind of look similar, but and actually does this pretty same job too, finding the attention between this. So we'll be essentially what we'll be doing is, after training the model, let's say after each epoch, this is how we define our loss function. What we'll be doing is, we'll be like taking this image, right? We will for diagrammatical representation, I have drawn this little chart. You could just follow that. We could just follow. What we'll be doing is, we'll just for each image, we'll be passing this image through the image encoder. We'll be passing this text to the text encoder, and we'll be multiplying or finding the dot product. A big dot there, right? I'm going to draw a bit dot there. So we'll be getting the dot product of both of these values, the output of the text encoder and the image encoder for each pair, and I'm going to determine a value. This is going to be X, or something like a probably shaded area. So this shaded area represents like the value. If it is more shaded, then it is probably a huge value. And we want like each pair to we want the diagonal to actually have like huge values. It's going to be pretty small, because this the image of the boy and the text skinny dog are not similar, right? So we want this output to be as low as possible, because this image corresponds to the happy boy. And then this is going to be way lower than that. Then this also very low. But here we want this to be as dark as possible. We essentially want the diagonals to be as dark as possible, right? This will be like lower. Also, now this will be lower. This will be way higher. So we want the diagonals to be as high value as possible, right? So these are like numericals, by the way. They're not like diagrammatical or images, as we are dealing with stable diffusion. Don't think they are images. They are just values determining if they are more shaded, then higher value. So we want the diagonal to be as thick as possible compared to the other models. So to actually design a loss function from this chart, what we could do is, we could just take this diagonal, right? For example, X, right? We can just take an X and subtract it by all of these values, right? So what we could do is, you could just take these X values, and these are just numbers, by the way. These are just mere numbers. You could just add all of these numbers, add all of the numbers from the diagonal, and we could just subtract them from the sum of all of these other numbers. By this, we could design a loss function which makes sure that we make the diagonal as thick as possible. And so we could just input this loss function to the text encoder and the image encoder, right? Or just text encoder, because we only care about the text encoder, right? We don't want the image encoder, right? We are only taking text as input, right? So we'll be taking the text encoder, we'll be training its weights such that this loss function, the loss function, this loss function, x2 something like that, right? We want this for loss function to be as low as possible, right? Therefore, we will be making training this text encoder such that this loss function is as low as possible. So that is the idea we'll be talking about. That is a loss function that we'll also be using. So hope you're understanding everything that is going on here. Nothing actually pretty complex, right? Pretty straightforward. So thank you for watching. I'll see you in the next video. So, and please stick with me. I'll probably make this probably very good, very informative series as possible, right? And then yeah, goodbye.